we're able to rewrite the Schrodinger equation in an integrated form using the Green's function. The Green's function basically allows you to invert these two terms. Yeah, indeed, if we multiply through by 2m over h bar squared, we get minus this guy, and we can put the minus k squared over to this side, and we could put the v over on this side. Of course, it's all multiplied through. This, we can do that. And now all we do is we invert this operator using a Green's function. And we get a solution for the scattering wave function, and it's written in a recursive fashion. Now remember that you can add a plane wave over on this side, and that doesn't change anything because a plane wave being acted on by this thing just gives you 0. So we added a plane wave, and that kind of helps us with our boundary condition that we have an incoming plane wave, and then you have 2m over h bar squared integral dr, and then this Green's function. But it's not really any different from the Schrodinger equation. You just invert the Schrodinger equation and use the Green's function. This is, equal to, in position representation, the inverse of this operator, using the appropriate boundary condition that you have an outgoing spherical wave. So we saw that one of the solutions that corresponds to scattering for this inverse operator is the one that has to be used here is minus 1 over 4 pi e to the I k magnitude of r minus r prime over r minus r prime, like that. So that's kind of the situation, and we're gonna now talk about solutions to this rewritten form of Schrodinger's equation a little more formally. But any questions about that? Because that's a sort of important setup. Okay, so we can rewrite, if we don't write this out in coordinate space, we can of course write the same equation. And again, this is called the Lippmann Schwinger equation. If we don't write it out in terms of coordinate representation, we can write it in terms of kets as just vectors in our Hilbert space. And in that case, it will look like the following. Okay, so that's the Green's function. It's just a direct mapping here. This guy is that guy with the factors of 2m over h bar squared. That gives you that inverse operator. And then this guy is that guy, and that guy is this guy. So it's all the same except written in terms of operators and vectors instead of the coordinate representation. You could go from one to the other by just moving the coordinate representation. And I told you I was going to tell you what this is about. This is the thing that picks out the right boundary condition for the screens function. I'll show you how in a moment. But in principle, what we left off with last time, I told you that you can solve this equation recursively by you keep substituting in for this psi plus here using, assuming that v is small. So if v is small, then to leading order, you just have the incoming wave. And so to next order in v, you could substitute in this guy into the integral, and then you'd get the Born approximation, which is what I showed you last time. But you can keep doing this recursive procedure, and it's easier to think about it in terms of these operators here. So again, let's start writing out this recursive procedure. To leading order, you get, and H naught here is just the kinetic energy. It should be sort of reminiscent of the Dyson series in some sense, what we did for time-dependent perturbation theory. It has the same kind of structure where we just back substitute in the previous solution. So to leading order in V, you just substitute in this guy K. So this would be the Born approximation, which you looked at in a different way for using Fermi's golden rule, but it's the same thing. Get that same expression. But of course, you can go further. You can now substitute in this whole thing into psi of k, and you would get the next leading order, or the next order in this Born series, as it's called, which would just be two of these propagators put in there, and you can keep going. You can add more, and there's even a graphical representation for this. It's the following. You can denote this guy as a propagator, and a factor of the potential will come in as this kind of squiggly line. So this is V, and this is 1 over. So you can get something that's actually akin to perturbation theory. But before I get there, let's see. What can I say about it? So this series, in a sense, it so let's see. Yeah, so for instance, this guy, you can sort of draw it as propagator, and then the potential, this guy right here, you'll get 2 propagators and 2 factors of the potential, and it always sort of terminates on the potential. Then for the next term, you would get 3 propagators and 3 potentials, and so on. So you could set up a graphical representation of these terms if you wanted. But they're kind of easy to think about without the graphical representation. Just each time you go to the next term, you'll pick up another factor of a propagator and the potential. And if you were to sum up all those terms, you would, of course, there's always a propagator out front. And then there's this matrix T, which would include the effects of all of the potentials, all of the higher order terms. So this is called the T matrix. And in terms of the potential, of course, the leading word is just a potential. That's, again, the Born approximation. But then you can add corrections to this, which as follows. And so on. So again, each time you go to the next term, you just sandwich in an extra propagator and a V, and then the thing is always bracketed on both sides by V. So it's a power series in the potential V. All right, so you can actually get corrections now to the Born approximation that include higher powers of the scattering potential. And this thing is called the T matrix. It'll be important, as we'll see. And in some sense, if you know the T matrix exactly, then you know the exact solution to your scattering problem, because you'll get now a full. If you know the T matrix, then you have an exact solution to the scattering problem, right? You would have solved this sort of iteratively. So, but it's unclear that you can sum up this infinite series, or if it converges. So there's issues with that. But formally speaking, this is a solution to the scattering problem. So there you have it. And now let's figure out why we needed this plus I epsilon. It's, of course, easiest to see in coordinate space. And so let's put in some coordinate kets. And we'll look at plus or minus I epsilon. We'll see that the minus I epsilon gives you the other Green's function that corresponds to spherically incoming waves. So we do R prime and R double prime, and we'll define R as R double prime minus R prime. As we'll see, that will be a convenient notation. And all we do here is just put in, the Green's function. There's that 2m over h bar squared. There's, we can add a completeness relation in terms of the momentum, or equivalently the wave vectors. And we get e to the I k dot r over k squared. That's from e minus k, or let's call this something else, maybe k bar. Yeah, k bar vector, maybe. Yeah. Or maybe it's easier to call it k prime. Yeah, why not? We'll call it k prime. So this is the magnitude of k squared plus or minus I epsilon. So that's what it is. I'm skipping some steps because you should be very comfortable now going to position space. Again, you just put in some momentum, completeness relations, then you know how the h naught, which is just the kinetic energy, acts on momentum. It gives you a factor of k squared over h bar squared k squared over 2m. So that's how you get these guys. E is equal to, so this is for an incoming energy equal to this. And so everything else kind of follows from that. So I'm skipping that step because you should be comfortable with that. Just adding some completenesses here on both sides. This is, and then, rewriting this inverse operator in terms of coordinate representation. And again, this is in momentum space, it's really easy because this is a constant and this is also a constant because in momentum space, the kinetic energy is diagonalized. It's just p squared over 2m or h bar squared k squared over 2m. Anyway, so you have that. So now you can actually just do this integral over k prime. You have just one direction you have to worry about, which is r, which again is the difference between these two guys. So there's a factor of 2 pi that just comes out from the integration over phi. So you get an integration over theta and integration over the magnitude of k prime. One of these factors of 2 pi cancels, and you get k prime squared sine theta. That's from the measure, spherical coordinate stuff. You get e to the I k prime r cosine theta. You make r along the z-axis, and then you have k squared minus k prime squared plus or minus I epsilon. And at this point, you could do the integration over the theta, and that's just done. The u substitution, u is cosine theta, so du sine theta d theta. So that's pretty straightforward, and you just get an exponential integral, and you get m over 2 pi squared h bar squared integral from 0 to infinity. You've got the dk prime left over, got the k prime squared over k squared, k prime squared. All right, so you can just do this exponential integral. And another thing to note is that this integration over k prime is even. This thing is an even function of k prime, so we can extend the limits of integration from minus infinity to infinity. So in the end, you get m over 2 pi squared I r h bar squared. That just comes from doing this. You get a 1 over I r k prime here and times the exponential. But so the leftover stuff is an integral from. Oh, so it's a little bit, yeah. So this is an even function of k prime, but this you can work out. What it gives you a sign, which you can break up into. You can break it up into two pieces, but in the end, you can combine those two pieces into one integral that goes from minus infinity to infinity, and it's dk prime. One of the factors of k prime cancels just from this integration, and you get k prime over here. You get an e to the I k prime r. That's from, again, the leftover thing here. And all of this divided by k squared minus k prime squared plus or minus I epsilon. So that's the integral you're left with. And the idea here is that you would do this integral using a contour, right? You're in the complex K prime plane, your integration's over here. And you could close the contour upstairs like that, because we know for if K prime is a large imaginary part, then this exponential will be large and negative in the exponent. And so this will be, you'll have a suppressed, this will be exponentially suppressed up here. And so what happens is that we look for poles of this thing in order to figure out what the value of this contour integral is. So you look for places where the denominator vanishes. And what you'll notice is that if epsilon is equal to 0, then this integral becomes ill-defined because this denominator vanishes when k squared is equal to k prime squared, or k prime is equal to plus or minus k. But that's not good because those poles lie along the real axis, right? It'll be here and here, minus k and plus k. So that's not good because our integral contour would go straight through it along the real axis, so that integration is blows up, it's not defined. And so that's why you need this plus or minus I epsilon. It it gives the poles an imaginary part, and depending on the sign, whether it's plus I epsilon or minus I epsilon, it'll shift the two poles in sort of opposite directions. You either pick up, for plus I epsilon, you'll pick up this pole because this guy gets shifted down up and this guy gets shifted down. So that's for plus I epsilon. For minus I epsilon, it's sort of the opposite situation where this guy gets shifted up and this guy gets shifted down, for minus I epsilon, that case. So you pick up either the pole at plus k or the pole at minus k, depending on which plus or minus I epsilon you have. And that selects which Green's function you get, because if you put either plus or minus depending on whether you put plus or minus k prime here, right? If you put plus k prime, you'll get the outgoing spherical wave. If you put the minus k here, if you put the value of k prime at the pole, it's either plus or minus k, right? Either this one or this one. If you put plus k, then it's the outgoing spherical wave. If you put minus k, it's the incoming spherical wave. So that selects whether you get one Green's function or the other one. And so in the end, you'll get minus, and remember it's times 2 pi I times the residue and so on. So in the end, you can calculate it out to be m over 2 pi. One of the pi's cancels because of the 2 pi I times the residue business for the contour integral. And you get the magnitude here, r. That's just this guy right here, the r. And you get the exponential e plus or minus I k r, depending on whether you pick up or down, right, for the whether you pick up or down for the, or plus or minus I epsilon in the denominator here. So that's what you get. And if you look back to the Green's functions that we had, this is exactly the right form. It's it's this guy, right? Minus 1 over 4 pi e to the I k r over r. And then there's an extra factor of 2m over h bar squared. So all in all, you just get this m over h bar squared, factor of 2 cancels, gives you a 2 there, and then you get plus or minus ikr over r. So this is indeed the right Green's function. You have to pick the plus I epsilon in order to pick out the right boundary condition that you have outgoing spherical waves. So these are the G plus or minuses that we introduced. And it's kind of nice, right? This is a sort of way of proving that instead of doing guess and check, right, that these guys really are the right Green's functions. Here we did this inverse explicitly in coordinate space or in momentum space. So this all kind of checks out. That we have the right Green's function and so on. So any questions about that? And now that you know how this works for this, you could of course go back here and sandwich this between two position kets, and then stick in a bunch of completeness relations and work out what the higher order corrections are to the Born approximation if you wanted. Any questions though? Okay, well, so now we've sort of shown why the plus I epsilon. And the last important thing to talk about to connect back to the partial wave expansion is the S matrix. And remember back in the partial waves, we said S matrix has something to do with the phase shifts and so on, but let's talk about it generally in this context. And the S matrix, all it is actually, in operator language, it's the interaction picture evolution operator that goes from the far past to the far future. And again, and I've drawn this kind of picture before. The idea is what is scattering? You have a target here, and you are coming in with some initial momentum K, and far in the past, you just have a free particle with some momentum. It's localized some fashion, but you have some wave packet that you send in to your target at the target location. It interacts with some potential, right? And then the thing gets scattered. And far in the distant future, you detect this thing that's moving out with some K prime. And what the S matrix tells you is just the interaction picture time evolution for that process, where far in the distant past, you have a free particle. Then at around t equals 0, that time you interact with the target potential, and then in the distant future, you scatter away. So what you want to do is actually you can use time-dependent perturbation theory to understand this. And you just want to introduce the appropriate time-dependent perturbation. And the appropriate one to use is the following: e to the eta t v of r, the scattering potential, where eta is going to be sent to 0. It's going to be a small positive number that you send to 0 at the end of the calculation. So why do you want such a thing? Well, this is very convenient because, as you send eta to 0, of course, the perturbation will be v, but you want it set up in such a way that far in the distant past, you don't have, this thing is far away and not interacting with the potential. So you want it to just experience no potential there. So you can use this perturbation to kind of rig that particular boundary condition that you're coming in as the free particle here. So you see if eta is positive, then as t goes to negative infinity, this thing just becomes 0. So it kind of sets up the boundary condition for you, the right one. We'll see that it's equivalent to actually choosing, this eta is equivalent to choosing a positive epsilon here. And we'll see how, because it comes directly out of perturbation theory, the time-dependent perturbation theory. Because we know that we can just start writing down the time-dependent perturbation theory for you. We can write down the Dyson series. And the first term is the identity, and then it's minus I over h bar, integral from minus infinity to infinity, dt e to the I, h naught t over h bar, and we have our v e to the eta t. Remember that you have to write the perturbation in the interaction picture, so you sandwich it between these phase factors. Then you get second order stuff. We could write it out, I guess, minus infinity to infinity. I'm not going to do the time ordering one. I'm just going to write down the nested integrals. So we've got the nested integral here that goes from minus infinity to t. Now this is dt prime. Remember that you need the time order properly, or alternatively have these nested integrals or t prime stays smaller than t, because the operator that acts first must be the one that has an earlier time. You just go back to the time-dependent perturbation theory notes, you'll see that. So you get this kind of thing. And so on. You get the higher order terms. But of course, you can evaluate all this in terms of your free particle states to sort of see what's going on. You can look at the momentum space representation of this. So if we look at that, if we look at this guy, then we can start seeing how this is connected to the Born series. So let's look at this first term here in momentum space. So if we're to do that, then of course the only thing, and why momentum space? Because these are diagonal in momentum space. So if we look at that term, then that term is equal to, well, first of all, we'll get the identity is going to be just a delta function between k prime and k. That's easy because it's just the identity. So you just get the dot product between these. But the next term is kind of interesting. You get minus I over h bar. And then, of course, these guys are eigenstates of momentum. So we can replace them with numbers. And the only thing that has any kind of operator dependence is the V portion. But the V is just some position-dependent scattering potential. So whatever this matrix element is, it just comes out and doesn't hurt anybody. So you just pull it out of the integral. And what you're left with is IT over H bar, and then you get the energy associated with K prime momentum. That would be this guy acting on the bra, K prime, and this guy acting on the ket will give you a minus EK factor. And then all of that is multiplied by A to T from this guy. So, okay, but you can actually do this integration, and the idea is that that at long times, or the idea is that this thing, see, we're integrating an oscillating thing around from minus infinity to infinity. And the only contributions to this thing will come from the place where the exponent in here vanishes. So you can actually show that this integration here, and maybe this will, I'll assign this to show this kind of thing as this is very similar to what happened in the derivation for the Fermi's golden rule. But I don't want to get into it, so it'll be part of homework 4, I think. You'll show that this integration is equal to a delta function, 1 over H bar, stuff in here, EK prime minus EK. And then it's minus IH bar eta. But eta will go to 0 after we finish our calculation. So this will just go away. And there's also a factor of 2 pi. So this is 2 pi. If you go back to the notes, there's a very similar derivation where you have this exponential kind of integral when we're doing Fermi's golden rule, but you'll get some practice proving this kind of thing. So you get that. And good. So now things get a little bit trickier when we deal with this next order term. So far we just have the first 2 terms, and but we'll need to go. We'll need to go a little bit further to really get things going. So, and by the way, you can factor out the 1 over H bar from everything, which comes in as an H bar in the numerator just from the way the delta function works. And then this, again, in the limit that eta is small, you just get this guy. And kind of not surprising, this delta function just tells you that the outgoing momentum, the energy, the outgoing energy has to be equal to the incoming energy. It's just a statement of energy conservation. This first term is sort of like momentum conservation. And then this next term, when you include the effect of the potential, what it tells you is that although momentum, the direction might change. You still get this term is proportional to this delta function, which tells you that the energy can't change. And that's what we would expect from sort of inelastic scattering problem. So that's the physics of it. So now we can go and do the next term, which is more complicated, but so it goes. So we'll look at this term right here to see what happens. And let me call this I or something, just to make things a little more notation, a little bit more compact. So what's I? Well, you got your minus infinity to infinity dt, and then you've got, you now need to include you'll need to include a completeness relation in momentum, so you can sandwich it between the two v's here. You need to sandwich in an integral over k, because you want everything to be written in terms of the momentum space representation. So you want to split apart the two v's. So what do you get? You get an integration over, let's call it, I don't want to call it k prime. I guess I'll call it k bar vector. It's a little bit awkward, but so it goes. I don't want to have too many primes, so I don't want to do double prime. But anyway, so all of the exponential factors, they're of course eigenstates of momentum. So they all come in, and let's put omegas instead of, to cancel out that h bar. So you get omega k prime minus omega k bar times t plus eta t. So if we stick in the k bar place here, right, then this factor x on the k bar gives me a factor of minus omega k bar t. And then this guy on the left, of course, it'll give us a k prime. So I here is just this term sandwiched. It's this term sandwiched between k prime. This is all this stuff in here. It's just these guys like this. So that gives us this I omega k prime here. And then we have k prime v k bar. That's the first matrix element. Then we have the minus infinity to t dt prime. And now we have more exponential factors, e to the I. This time we have an omega k bar as our ket, or as our bra, which this guy acts on, this guy. Then we have a minus, this term acts on the k, so you get a minus omega k. This is all acting on t prime. Then you have a plus eta t prime. And then you have your other matrix element, which is k bar v k. Okay. So that's just sticking in the completeness, putting in the exponential factors, because the h naughts are all, they're just a kinetic energy, so they're diagonal and momentum. And from here, you can actually do the integration over t prime. You can do this integration because all the t prime stuff is just here, right? You can do that integral. And what you get is integration minus infinity to infinity dt d3k vector. Of course, these all have vectors on them. You got these terms, which I'll leave here. You got the k vector vk part. And then when you do this integration over t prime, of course, this matrix element comes out also. It doesn't depend on time. But doing this leftover integration over t prime, what you get is e to the I omega k bar minus omega k t prime plus eta t prime divided by all this stuff I omega k bar minus omega k plus eta. And it's evaluated between t prime minus infinity to t, right? And now you can start to see that this denominator looks an awful lot like the Green's function denominator we had all the way back up here. Remember, the omegas are just e over h bar, so they are up to a factor of m here, just k squareds. And then if I factor out an I here, you see you would get sort of, well, minus I times this stuff plus or minus epsilon, or plus epsilon here. And here it's the same, we get a plus eta. So this denominator should be very familiar to you from the Green's function. It looks very similar, except we have a time variable now that we're evaluating it between. And the time variable is just these limits of integration from minus infinity to t. And the nice thing, if you pick positive eta here, then if you send t prime to minus infinity, then that part just vanishes. So all you need is just this guy, the one evaluated at t. So that's good. And let's see. And so if you keep the one evaluated at t, and this term, this part of the integration just gives you 0, what you're left with is just the leftover integral over t, which is going to be well, let's see, it's going to be minus infinity to infinity dt of e to the I omega k prime minus omega k bar t plus eta t. And then you'll also get these guys. So you'll get the plus I omega k bar minus omega k t plus eta t in the exponent. So that's the leftover times all the other stuff that's left over. These matrix elements and this leftover integration over momentum and so on. But in terms of finishing up the time integral, you see now that some stuff cancels, right? This omega k will cancel this omega k like that. And these two guys combine to get, a factor of 2. And so that all that does is it just reduces this integration to an integral that we had before, minus infinity to infinity of e to the I omega k prime minus omega k t plus 2 eta t. And if you look, this integration right here is the same as the integration we had for the first term up here, this guy. The e over h bar is just the omegas. It's k prime minus k plus eta t. Now we have 2 eta t, but remember we're just sending that to 0 anyway. So we have that this integration here, it's the same as this one. These two guys in blue here. So this whole thing has to be equal to 2 pi h bar delta ek prime minus ek. So let's put it all together now. The first order and the second order terms. Let's put it all together, and I'm going to rewrite it here. So what do we get? We get in the momentum space representation, you get a delta function in k. Then you get minus 2 pi I delta function in the energies times this matrix element k prime vk. And then you get same thing, minus 2 pi I delta ek prime minus ek. And then you have the leftover integration over k bar for the second order term. And what's in that is there's two matrix elements. So this is k bar, vk. And then we have this leftover denominator. We have this leftover denominator here. Remember, we never dealt with this. We just pulled out this exponential because that's the only thing that depends on t. And we did the exponential integral, but we're still left with this denominator right here. And that denominator, which we pulled out this factor of I to give us a minus I here. So the denominator that's left over is E is EK minus EK bar plus I eta. All right, and the h bar is canceled here. Remember, omega is E over h bar. The h bar is canceled, this h bar here, that was part of the delta function. You got the 2 pi, the h bar canceled, the h bar associated with going from omega to E. Okay, so you have this, and so that's pretty good, because now you see the form of this thing, right? We have a delta function minus 2 pi I delta function in the energies times this term minus 2 pi I delta function times this integration, which is a product of these two matrix elements over this denominator, which looks exactly like now the Green's function denominator, right? These are just k squareds. If we put in these are just h bar squareds, k squareds over 2m. So what we found is that, and remember all of this is just the S matrix in momentum space. What we found is that this whole thing is equal to, and so on. You can do the higher order terms, and you can convince yourself pretty quickly that all those higher order terms are nothing but just the higher order terms in the Born series. So if we look at this, all this is just the momentum space representation of the T matrix. If we go back somewhere, I promised the T matrix would show up again. You see the first term is V. So if we sandwich this T matrix between K prime and K, we'll get just the matrix element of V first. The second order term would be a product of two matrix elements of V with a propagator inside. And that's exactly what this term is. Two matrix elements sandwiched between K prime and K with a completeness in here that takes care of diagonalizing the propagator portion, which just gives us this. And instead of plus I epsilon, we just have a plus I eta, but it's still just a small number that we send to 0. So in the end, you can show that this whole thing is 2 pi I delta function in energy, which is a statement of energy conservation, times the momentum space representation of the T matrix. So this is really a beautiful result. It sort of connects this time-dependent perturbation theory approach to the Born series. It tells you that the S matrix really is related to the Born series. So yeah. Any questions about that? On the notes, I give a few more steps in the derivation, I guess, but you'll practice some of this on your homework. There's not too much to it. Again, so you start with the time-dependent perturbation theory results that we had, and instead of using any regular perturbation, you use this one. And then you put everything in momentum space because your H naught is diagonal in momentum space. So it turns all the e to the I H naught stuff into e to the I omega. And then it's a kind of delicate procedure, but if you get all the limits right, all the time integrations just become exponential integrals. And the stuff in the exponent, when you integrate it, it goes into the denominator like this, and that's what provides the factors of the propagators. And you can really just look at it, and we know that we worked out the time-dependent perturbation theory, the terms to arbitrary order. You can look at each one, and you'll see a pattern develop, namely that each of the terms looks like the following. You get 2 pi I times the delta function in the energies, that's energy conservation. And this delta function always comes from that last integral over time, that outside integral, this last one over t, which always is going to have this form. You have different factors of plus eta here. You'll have, for the next order term, you'll have 3 plus 3 eta t. But we send eta to 0 at the end of the calculation, so that's okay. That won't influence the result of this integration. You still just pick up this delta function in energy. And then the rest of the stuff that's left over is just however many completeness relations you need to put in to break up the V's. And you'll get a bunch of these denominators, which are going to be the Green's functions. And so in the end, what you're left with is that this equation here, that very important equation that in momentum space, the S matrix, all it is just delta function minus 2 pi I delta function in energy, which is a statement of energy conservation for elastic scattering, times the T matrix. So that's the connection between S and T, and a connection between time-dependent perturbation theory and the Born approximation. So it's nice. And again, this eta plays the same role as the plus I epsilon did in the Born approximation. So all these pictures are consistent with each other and give you different ways of looking at scattering as a kind of time-dependent perturbation theory problem, as just a regular perturbation theory problem in terms of when we did the Born series. And the S matrix is the kind of the thing that connects the time-dependent problem to the time-independent problem in this fashion. Because remember, the S matrix, it's defined as the two formulas that we have so far for the class, for this class, is that the S matrix is the interaction picture unitary evolution operator. Okay, so what else can we say about the T matrix? Well, there's some more formulas that we could really. So this is one way the T matrix is connected to the S matrix. Again, the T matrix itself up here gives you this Born series here. We could say some more. Again, look, this T matrix is related to the solution for the scattering wave function. So that's good. So there's more relations you can write down regarding the T matrix. One is that T acting on K has to be equal to V acting on psi K, the full solution. So that's another thing. And now you could sandwich this between K prime. So this, let me put little vectors here. So this thing is also equal to K prime V psi K plus, so this is also a kind of relationship you have. So you can also write this S matrix in terms of the full scattering solution if you wanted. And we can actually also connect this back to the scattering amplitude. Because remember, the scattering amplitude remember that the scattering amplitude is just this stuff here. In terms of the exact solution to the Schrodinger equation. So the T matrix is also, of course, related to the scattering amplitude. So another thing we can write down is the scattering amplitude, which is the thing we did the partial wave expansion for. It's minus m over 2 pi h bar squared dr prime e to the minus I k r hat r prime. This is something we derived, I think, the last class. V of r prime. And in the Born approximation, we would have put just a plane wave here, e to the ikr, but generally it's the full scattering solution. This part, remember, comes from G plus far away. So this was the scattering amplitude, but this is nothing but if you use boxed normalized wave functions for momentum, then the other way we can write this is m L cubed over 2 pi h bar squared. And now we can write this integral as just a dot product between, or the matrix element between this guy. And again, this is assuming that the wave functions are normalized as 1 over L to the 3/2. It allows us to write things this way. Then we can write this matrix element as just the following, right? Because all this is a plane wave in the K prime direction. Remember, K prime vector, it points along R prime, points along R hat, sorry, and has same magnitude as K. So this is just K prime. So this is just a direct, and this L cubed is to give the right normalization to these plane waves. And so you just get this. And this is nothing but, again, using this formula, this is minus ml cubed over 2 pi h bar squared k prime t. Okay, so that's another important relationship for the T matrix. It just also gives you the scattering amplitude. So yeah, and notice that if you replace T with V, then you just get the Born approximation for scattering. And the higher order terms give you the corrections to the Born approximation. So I'll leave it here for now, and then we'll continue talking about the S matrix a little bit and its symmetries. But this is the sort of important formulas you have that connect the T matrix to both the S matrix and the scattering amplitude. And remember, the T matrix is just this formal sum of, of the Born series, where you get higher and higher order corrections to the Born series from iteratively solving the Lippmann-Schwinger equation. Okay, yeah, so that's it for today. And next time we'll talk more about the S matrix and what it can tell you about the scattering problem.